Hi, I'm Brendan Haycock, the project manager.
Hi, I'm Kyle Sines, the system engineer.
And we are the leaders of the Rover team, Team Argon, representing the University of Michigan-Dearborn.
This is our second year as a team and our first year attempting University Rover Challenge.
A fundamental aspect of this competition is geology, and it is one of the main purposes for designing this rover. The design process of this rover closely parallels the design processes of actual Mars rovers and uses actual Mars science. The soil type at the competition site is most likely desert soil. This soil type is characterized as being very hard. To combat this, we're going to use an auger to drill to the depth of 10 centimeters and collect the sample, rather than trying to scoop it out. In an effort to choose a location for the science task, we have been actively looking at maps of the competition region, such as this topographic map made by the U.S. Geological Survey. We have also been looking at maps made with Landsat spectral data, such as this image of the area surrounding the competition site, and this higher resolution image of the area surrounding the MDRS. From studying geologic maps, it appears that the cooler colors are indicative of marine sediments, while the warmer colors are coarser grain material, such as fluvial deposits. We are actively continuing our search to find better and higher resolution data to find the best possible sites for this investigation.
Our rover implements a rocker bogie design. Using two stages, the rockers employ all triangular angles to disperse forces. One end of a rocker is fitted with a drive wheel, and the other end is pivoted to a bogie. The rockers are connected to each other and the vehicle chassis through a degree of difference. Relative to the chassis, when one rocker goes up, the other goes down. The chassis maintains the average angle of both rockers. On the larger legs for the design, two springs are fixed to the chassis to absorb shock. The springs also act as a safeguard to prevent the body from inverting into itself. This would thwart the rover from immobilization and allow all 6 wheels to remain on the ground while tackling obstacles. After analyzing wheel features, we determined that it was necessary to purchase our wheels based on tread design, weight capacity, and size. After going through all the options, we decided on purchasing Sandtrax kayak wheels. These wheels are puncture-free, have a load of 80 kilograms, and the open-air design allows for a lighter tire while still maintaining strength.
So for the rover's powertrain, we have 6 in-hub U816 Tiger motors. These motors produce 1 Nm torque each. To raise the torque, we have these gearboxes that have a gear reduction of 4:1 each. We're using 2 of these together so that we get an output torque of 16 Nm on each wheel. This kind of output torque is enough to help the rover traverse through sand and climb steep grades that is required in the competition.
Over extensive research, our team has come up with a robotic arm centered around a mass and pulley system. This system helps provide our team with a mechanical advantage and providing us with minimal input effort and maximum force output.
Our overall design contains multiple servo motors used in conjunction with pulse width modulators, or PWMs, combined with 6 degrees of freedom, 3 degrees of robotic arm, and 3 degrees of robotic hand. The whole of the design is used with a combination of aluminum due to its high strength to weight ratio and extruded plastic via 3D printing, allowing a greater variation of design and reducing the overall weight of the rover.
We're using 36 volts and 20 amp hours in our battery pack, and it's comprised of 18650 cells, and based on our calculations, this is plenty of power to complete the entire competition.
With our open source electronic speed controller, we have successfully implemented current limiting and regenerative braking. Our electrical safety system consists of a manual emergency stop button as well as a wireless key fob and a MOSFET controlled ground. For our observation and data collection during the science task, we will be using digital temperature, humidity, and acidity sensors.
Our approach toward the software development of our rover uses a framework that the parent club on our campus is currently transitioning towards called Robotic Operating System, or ROS. The software is built on top of Ubuntu Linux and is a modular, multi-language framework. The underlying code of the framework will be based upon C and C++ languages. Due to its modular nature, the software is being pieced together using existing code from other projects in our club, such as the Xbox 360 control node.
So to complete the challenge of autonomous terrain traversal, we will be using a LiDAR, an IMU, computer vision, as well as the GPS. Our path planning will be primarily dependent on the GPS, adjusting as needed with changes in terrain and slope.
We've been working hard on the rover for the past 6 months. We are on time for completion and have ample time for testing.
From the Rover team representing the University of Michigan-Dearborn, we'd like to thank you for your consideration.